Our universe is a strange and mysterious place, governed by laws that often seem to contradict each other. On one hand, we have quantum mechanics, the theory that describes the wacky world of atoms and subatomic particles. Quantum mechanics tells us that the universe is fundamentally uncertain, with particles existing in multiple states at once. On the other hand, we have Einstein's theory of general relativity, which explains the large-scale structure of the universe, including gravity. General relativity paints a picture of a smooth, continuous spacetime warped by massive objects like stars and black holes. So far, so good, right? Except these two pillars of modern physics seem fundamentally incompatible. Quantum mechanics thrives on the probabilistic nature of the universe, while general relativity demands a smooth, deterministic reality. This clash of titans plays out most dramatically in the extreme environments of black holes, where gravity is so strong that not even light can escape. And it's here, at the edge of reality, that we encounter the perplexing firewall paradox. Imagine a giant cosmic vacuum cleaner, relentlessly sucking in everything that gets too close. That's essentially what a black hole is, a region of space-time where gravity is so intense that nothing, not even light, can escape its clutches. The boundary of a black hole is known as the event horizon, a point of no return beyond which escape is impossible. Once something crosses the event horizon, it's destined to be crushed into oblivion at the singularity, the infinitely dense heart of the black hole. Now, here's where things get really weird. According to general relativity, an observer falling into a black hole wouldn't notice anything special as they crossed the event horizon. It would be a smooth, uneventful journey, at least until they got spaghettified by the intense tidal forces near the singularity. However, this seemingly innocuous journey creates a major headache for quantum mechanics. You see, one of the fundamental tenets of quantum mechanics is that information cannot be destroyed. In other words, the universe keeps a perfect record of every particle and interaction, allowing us, in principle, to rewind the tape of time and reconstruct the past. But if information falls into a black hole, it seems to vanish from the universe forever, violating this fundamental principle. This conundrum is known as the black hole information paradox, and it has puzzled physicists for decades. For years, physicists thought they could resolve the information paradox by appealing to a gradual process of information leakage from black holes known as Hawking radiation. However, in 2012, a group of physicists dropped a bombshell that threw the entire field into disarray. They argued that resolving the information paradox while preserving both quantum mechanics and general relativity would require a radical sacrifice. The equivalence principle. This principle, a cornerstone of general relativity, states that the laws of physics are the same for all observers, regardless of their motion. To reconcile information conservation with quantum mechanics, these physicists proposed that the event horizon of a black hole is not a smooth, uneventful boundary as previously thought, but a raging inferno of high-energy particles they called a firewall. This firewall, they argued, would incinerate anything that dared to cross the event horizon, violating the equivalence principle and upending our understanding of black holes. The firewall paradox sent shockwaves through the physics community, forcing physicists to re-examine their assumptions about black holes and the nature of space-time itself. While the debate rages on, several promising solutions have emerged, each with its own set of implications. One intriguing solution proposes that black holes are not empty voids with an infinitely dense singularity at their center. Instead, they're more like giant fuzzy balls of quantum strings, the fundamental building blocks of matter according to string theory. In this fuzzball picture, there's no singularity and no empty space inside a black hole. Instead, the entire region within the event horizon is filled with a dense, tangled web of strings. This fuzzy structure would effectively blur the event horizon, eliminating the need for a firewall and preserving the equivalence principle. Section 5. Solution 2. Wormholes to the rescue. Another intriguing possibility is that black holes are connected to distant regions of space-time, or even other universes, through theoretical tunnels known as wormholes. These wormholes could act as shortcuts through space-time, allowing information that falls into a black hole to re-emerge elsewhere. While wormholes were once considered the stuff of science fiction, recent theoretical work has suggested that they might be more than just a figment of our imagination. In fact, some physicists believe that wormholes could provide a natural explanation for the strange interconnectedness of quantum entanglement. If black holes are indeed connected by wormholes, it's possible that information that falls into a black hole doesn't disappear, but instead travels through the wormhole to another part of the universe, preserving information conservation and avoiding the need for a firewall. Section 6. Solution 3. It's all about information, baby. A third solution to the firewall paradox comes from a radical shift in perspective. Instead of focusing on the physical properties of black holes, this approach emphasizes the fundamental nature of information itself. Proponents of this view argue that information is not just a passive passenger in the universe, but an active participant, shaping the very fabric of reality. In this framework, the event horizon of a black hole is not a physical boundary, but an information barrier, a point beyond which our classical description of space-time breaks down. This information-centric perspective suggests that the firewall paradox arises from our limited understanding of how information behaves in extreme gravitational environments. By developing a more complete theory of quantum gravity, one that unifies quantum mechanics and general relativity, we may finally be able to resolve this paradox and unlock the secrets of black holes. Section 7. Recent research. Peering into the abyss. In recent years, physicists have made significant strides in understanding the firewall paradox, thanks in part to advances in theoretical modeling and computational power. One promising avenue of research involves using sophisticated computer simulations to study the behavior of quantum fields in the vicinity of black holes. These simulations have provided tantalizing hints that the information falling into a black hole might not be destroyed after all, but rather encoded in subtle correlations within the Hawking radiation emitted by the black hole. This process, known as quantum hair, suggests that black holes might have more to them than meets the eye, carrying a faint imprint of the information they consume. Section 8. Experimental prospects. Catching a glimpse of the firewall. While the firewall paradox remains a theoretical puzzle for now, physicists are actively exploring ways to test these ideas experimentally. One ambitious proposal involves using a network of telescopes around the globe to image the event horizon of Sagittarius A, the supermassive black hole at the center of our Milky Way galaxy. By combining the light collected by these telescopes, astronomers hope to create a virtual telescope large enough to resolve the event horizon and potentially detect subtle distortions that could provide evidence for or against the existence of a firewall. Another experimental approach involves searching for signatures of Hawking radiation in laboratory settings. While detecting Hawking radiation from astrophysical black holes is currently beyond our technological capabilities, physicists are exploring ways to create analogs of black holes in the lab using ultra-cold atomic gases or other exotic materials. By studying the behavior of these analog black holes, researchers hope to gain insights into the quantum nature of gravity and potentially observe the subtle effects of Hawking radiation. Section 9. The future of physics, beyond the firewall. The firewall paradox is more than just an esoteric puzzle for theoretical physicists to ponder. It represents a fundamental challenge to our understanding of the universe and the laws that govern it. Resolving this paradox will likely require a profound shift in our perspective, leading to a new era of physics beyond Einstein and the Standard Model. Some physicists believe that the key to unlocking the secrets of the firewall paradox lies in developing a complete theory of quantum gravity, a theory that unifies quantum mechanics and general relativity into a single, coherent framework. String theory, loop quantum gravity, and other approaches to quantum gravity offer tantalizing glimpses of what such a theory might look like, but a complete and consistent theory remains elusive. If we can crack the code of quantum gravity and resolve the firewall paradox, it will have profound implications for our understanding of the universe, from the smallest subatomic particles to the largest cosmic structures. It could also pave the way for new technologies and innovations, as our understanding of the universe deepens and we unlock the secrets of the quantum realm. The journey to unravel the mysteries of the firewall paradox is just beginning, but it promises to be one of the most exciting and transformative adventures in the history of physics.